Good day. Today, I will explain the Python code shown, which demonstrates continuous time convolution using numerical methods. The main goal of this code is to define two signals, perform their convolution, and visualize the input signal and the resulting output. The code starts by importing the required libraries. NumPy is used for numerical operations and array handling. Matplotlib is used for plotting the signals, and the convol function from SciPy performs the convolution operation. These libraries are essential for signal processing simulations in Python. Next, the time axis is created. These lines generates 1000 equal space-time values from -5 seconds to +5 seconds. This time vector represents a continuous time signal that sampled finely enough to approximate continuity. Now, the first signal x of t is defined. This creates a rectangular pulse. The signal has a value of 1 between t is equal to 0 and t is equals to 2. It is 0 everywhere else. This means that x of t represents a finite duration input signal, which is common in a system analysis. Next, the impulse response of h of t is defined. This represents a casual exponential decay. The exponential function decays as time increases. This makes the system causal, meaning it does not respond before the input is applied. The code then computes the time step. This value represents the small time interval between samples and is necessary to properly scale the convolution so that it approximates the continuous time integral. Now, the convolution operation is performed. Mode is equals to full computes the entire convolution result. The multiplication by dt adjusts for numerical integration. The output y of t represents how the system responds to the input signal x of t. Next, a new time axis for the convolution output is created. Since convolution increases signal length, a new time vector is required so the input aligns correctly with time. The plotting section now begins. This sets the size of the figure to ensure clarity. The first subplot displays the input signal x of t. This graph shows a rectangular pulse, clearly illustrating when the signal is active. The second subplot displays the impulse response of h of t. This plot shows an exponentially decaying signal starting at t is equal to 0, confirming system causality. The third subplot shows the convolution output y of t. This graph represents the system output, which rises while the rectangular pulse overlaps with the exponential, then decays smoothly after the input ends. This behavior matches the theoretical expectation of convolution. Finally, the layout is adjusted and the plots are displayed. In summary, this code defines a rectangular input signal define a causal exponential impulse response, computes their convolution, and visualizes x of t, h of t, and y of t. This simulation helps us understand how linear time invariant systems respond to inputs using convolution.